All right, any questions on what's going on with the class? Any concepts or whatnot? Or just how the class is run? Homework 2 is due today. You guys should have seen the way to upload that on Canvas. Yeah. Yeah, the question was for things that have a MATLAB component, can you just submit the output? Yes, exactly. So I'm assuming you're referring to that question that was about like draw the vector diagram and stuff. Yeah, just give us the figure, paste it as an image or something. Was there a question over Zoom as well?
Yeah, I had one. Well, just on that, so we don't have to include like the code for or whatever script we use. I mean, I like added it into the PDF now, but for future, like we don't have to.
Yeah. Did the people in the room hear that? The question was just, do you have to post the code and stuff? And no, if the answer just asks you, if the question just asks you to plot the thing, then just plot it. That should be fine. If there might be questions later on in the future where it's like we are asking you to code up something or something like that, then go ahead. But we'll try and make that as clear as possible.
Okay, and then the other question I had, because we're obviously I'm assuming there's gonna be solutions posted to the homework eventually. Do we ever go over like any of the important questions in class, or ones that like are there any that are like worth discussing, or is that something that like we would discuss in office hours with you? Like, can we just show up and ask about that if we're interested?
The question is, are there any particularly important questions that we're going to discuss in the homework after the fact? Typically, no. Typically, the homework just happens. You guys are free to look at the solutions or something like that. If there are things that you guys are unclear about, I'll say that all the homework problems are kind of important. Like there's a reason why I assigned every homework problem that I gave you. I'm not just making you guys do stuff for the fun of it. And so I'm not going to go over all the different homeworks on here. That's what solutions are for. And then again, my office hours, the TA office hours and stuff, I'd be happy to go over anything that seems unclear to you guys. Speaking of office hours, my office hours is theoretically right after this class. I'm going to walk to my office after this class and have a setup something kind of like this. Although now that I think about it, I don't have a webcam in my office, so I'm probably not going to be able to draw on the screen and stuff like that. But I'll try and get something working for all of you guys. It's going to take me however long it takes to walk back to the office. It'll probably be the same link as this meeting is right now, not one of the 2 office hour links, which is scheduled for the other 2 time slots in the for office hours. You know, the TA office hours being 3 p.m. on Tuesdays and 7 p.m. on Mondays. Okay. Any other questions? Okay. Thanks for clarifying, everyone. Let me remind everyone where we were. On Monday, we basically got to, we finished our derivation of the different conservation laws. And so at the very end of even the class previous to Monday, so on Friday, we actually got to, or I guess in the middle of Monday's class, we got to this equation, which is Cauchy's momentum equation. Okay, and this came about because we figured out what this beast called the stress tensor was. And then we started applying that to different scenarios. For instance, we found that Cauchy's momentum equation you will then directly result in the hydrostatic equation that many of us were already familiar with. And if you weren't familiar with this particular format, then you know that pressure is equal to P0 minus rho GZ, or plus rho GH, or something like that, right? This is just, you know, how much head there is in a fluid or something like that. Then we started thinking about fluids in motion, and we realized that the stress tensor has contributions both from this hydrostatic component that we talked about above and the stress tensor, or the viscous stress tensor, sometimes called the deviatoric stress tensor. And when we plug this in, what we noticed was that along with the conservation of mass, or the continuity equation, and the momentum equation, which gave us 3 equations, we have 4 equations for what turns out to be 13 different unknowns in our fluids problem. And the question is, how do we actually get more equations to be able to actually solve our fluids problem exactly, right? Something that helped was that we determined that the stress tensor is going to be symmetric, and so we have 10 unknowns, but still we need 6 more equations, right? So before I can give you those equations, which will come about probably a little bit on Friday, I'm going to need to introduce one more concept And that has to do with the fundamentals of how actually, of how fluids, or how we keep track of fluids moving, basically. And this is because when fluids move, they undergo deformation. And so that's what I'm going to spend most of this class talking about. It's a pretty simple concept. I'm going to give myself a set of axes here, as we're all familiar with at this point. And I'm going to consider 2 points in my fluid that are kind of close together, but I'll call this point 1, and I'll call this point 2. And the question that I'm going to ask is, what happens to these 2 points, their relative positions and stuff, inside a flow field, right? This sort of stuff will become important because the way that we relate things like the stress tensor and velocities and stuff like that to one another to give us more of those equations, those 6 missing equations that we have that we just talked about at the beginning of class, has to deal with how stress is influenced by deformation and stuff like that. Okay, so to give ourselves a little bit more specificity, I'm going to call this first point x. It's going to be given by a position vector that goes from the origin to that point. That vector is going to be called x. Okay, and then this other point I'm going to call x plus the Greek letter xi. That. So in other words, what this implies, if you guys sort of know your like how vectors are added and stuff like that, is that this vector is xi. The vector connecting these two points is xi. Okay, so let me just write down in text what we were just talking about. We'll say consider 2 points in a flow field. Okay. Oops. In a flow field, if you guys can read that. Okay. We're going to say 1 at a position x, and then 0.2 at a position x plus c, like that. Okay. The question that I'm going to ask is, what happens to 1 and 2 and the line connecting them over time? Okay. Does that question kind of make sense to you guys? So in other words, I have 2 points and they're moving. And you might expect that if they're moving in a uniform velocity field, like if these 2 points have exactly the same velocity, then they're just going to move along like this. But you could imagine that if the velocity at point 1 is different than the velocity at point 2, then they could move relative to one another as well. And how are we going to tabulate all of those things, right? So in other words, another way of specifically talking about this line connecting them over time is basically, how is the fluid element or the fluid at x deformed? And that's why we're talking about deformation here. All right, so mathematically, we actually know how to deal with that. You know, we all talk about sort of small changes in position or time. You know, we've talked a lot in this class about little tiny cubes or little tiny pyramids and stuff like that, right? So what we're going to do now is we're going to apply a flow for a short time dt. Okay? And now let's look at what happens to our 2 points here. Our first point starts off at a position x, and then it's going to go to a new position. And that new position is going to be x plus v of x dt, right? V of x being, well, obviously the velocity field evaluated at x, right? The other point, we started off at x plus c. And that, well, it's not a surprise, is going to end up at a new position. Well, the original position, x plus c, now plus v evaluate x plus c dt. Yeah, pen's giving me trouble, sorry. dt. Okay. Now, as I mentioned, sort of in a hand-wavy way, if the velocity were uniform throughout my entire flow field here, then this would not be an interesting problem, because if my 2 points started here, they would both end up somewhere over here, and the relative positions are not going to be any different. Okay, but the key is that in general, the velocity at x plus c, that's a terrible c, not that they're in general that good anyway, could be different than at x. Okay, and so that's what we're going to mainly focus on right now. To figure out how the velocity is going to be different, well, we'll say that arc C could be small, and we will, whenever we're dealing with small things, we can think about Taylor expansions. Okay, so for instance, the first component of the velocity, v1, or you could call it the x component if you want, evaluated at x plus c, can be written in terms of the first component of the velocity at x, but then Taylor expanded, right? You would have dv1 dx1 times c1 plus dv1 dx2 times c2 plus dv1 dx3 times c3, and then all the higher order terms and stuff, right? This is just because, you know, velocity is a function of x1, x2, and x3, right? And so we have Taylor expand through all those different variables. Great. There's a compact way of writing this. Sorry, yeah, so this is v1, x1, but then these three terms, you can write those pretty easily together by just noticing that this is the dot product of c times the gradient of v1, right? Gradient of v1 is dvx1, is dv1 dx1 times e1 plus dvx times dv1 dx2 times e2, et cetera, and then c, you just take a dot product, right? And that's what you get. By analogy, I'm not going to go through this Taylor expansion 2 more times, but of course, this is going to be true for v2, the second component, and it's also going to be true for the third component. Okay? So I have basically 3 equations here, right? And while one way of compactly writing these 3 equations are basically exactly the same, except the index is just a little bit different, right? And each one, in this first equation, we're talking about v1, next one we're talking about v2, next one we're talking about v3, is that we could just write vj evaluated at x plus c is equal to vj of x plus, well, this dot product we can write like this. Right? Index notation. Remember, the rules of index notation is repeated indices you sum over, and that's what this dot product actually means, right? So you can see how, like, for instance, this top equation right here is basically just what you would get if you let j equal to 1. If you let j be 1 and you sum over here from I equals 1, 2, and 3, right? That's basically just index notation. Okay? Or if you don't like index notation, then this basically just says this. Okay? Was there a question over Zoom? Or did someone just, okay. Okay, does this all kind of make sense to you guys? You know, basically we just wrote the same equation for the 3 different components of V, and then we combine those equations, all those equations, into first using index notation, and then now using non-index notation. Okay. Notice how this guy right here is a tensor, right? The gradient of a vector is a tensor. So we have a tensor somehow in here, and I just kind of sneakily introduced a tensor without really telling you guys about it. And this just makes a lot of sense intuitively, right? It turns out that the reason why this works is specifically because we did we have 3 different equations for 1, 2, and 3. And so it's pretty obvious like what this tensor actually means. It's just that each of these the 3 components of this tensor is a vector, where those vectors are basically the gradient of v1, gradient of v2, and gradient of v3, right? And so the key to this whole, this is not a plus, that's an equals. The key to this whole deformation thing, and basically what velocity looks like at a distance slightly farther or at a slight distance away from our original point, is this velocity gradient tensor. Okay, this velocity gradient tensor looks something like this, if you prefer the matrix form. In terms of x's, y's, and z's, I can just write it out. It looks like that. Right? And as I mentioned, this is sort of the key. What this means is, in our deformation over here, or in the new positions of our 2 original points, 1 and 2, then we can substitute this definition of v at x plus c right here into this, and this is what we're going to get. Our first point, again, doesn't change. X goes from, or point 1 goes from x to x plus v of x dt. But then the second point goes from x plus c to x plus c plus v of x dt plus this. Okay. Now let me draw what that actually means. Okay. I keep pointing my 2 little fists and moving them around. Let me actually put that on paper at this point, or virtual paper, I guess. Our original 2 points looked something like this, right? They originally started off at x and x plus c. You could imagine connecting those together with a vector that looks like c, right? Here's 1, and here's 2. What we're saying is, if we move forward in velocity, then these 2 points are going to move, right? Let's say they move somewhere. You know what? Just for fun, let's have them all move all the way over to the right over here. Okay. This first point moves to a new location, x plus v of x dt. Okay. And the second point could move to a new location here. This point right here could be x plus c plus c plus v of x dt. That's what this point would be, right? And what's connecting those 2 points together is c, right? I'll call this point 1 prime and point 2 prime. Okay. But instead, that's not where it actually goes. It goes to a new point right here, to some other 2. Okay, I'll call this 2 double prime, and I'll call this 2 prime. Okay. This is where the new 2.2 actually is. And that's because this point is, this point right here is x plus c plus v of x dt plus this weird term right here that depends on the velocity gradient. And what that implies then is that this vector right here is actually my velocity gradient, right? That vector is c dot del v dt. That's what that vector actually is. And that's the change in relative position between 1 and 2 now, right? Before, there was no change in relative position, right? This object that just moved from here to here could essentially be a solid, right? In a solid, when a solid moves, every point just moves along with it. Okay, if it doesn't change in orientation, we'll get to that in a second. But if a solid is fixed in its orientation and fluid moves it along, or just for whatever reason it moves along, the Earth is moving around the sun or something like that, right? Every point relative to itself is the same. But here, because we're dealing with the fluid, and because the velocity at point 1 is slightly different than the velocity at point 2, then there's actually a relative motion, or there's a relative change between these 2 points. And that's what this is. Okay? And so let me write that out in a sentence. What this says is that, if I can actually spell and write, neighboring points change their relative positions in the presence of a velocity gradient. Okay. So this velocity gradient tensor is what actually encapsulates everything there is to know about deformation. And so we need to look a little bit more deeply at what that actually is. Any questions on this sort of concept of velocity gradient? This is sort of the complete underpinning of what deformation actually comes about. Did you have your hand up? So the question is, do you ever only need the diagonal of this velocity gradient tensor because we're just dotting it with C? No, when you're dotting it, you actually use all the components of it. And what I'm about to show you is that there are different contributions to this that actually depends on all the different components of this. I'm not sure why you think that when you dot it with a vector, you only use the diagonal. Yeah, exactly. So what he said is basically Adrian, right? Yeah. So what Adrian said was just that when you dot a vector with a tensor, the answer is a vector. So you might think, oh, you actually only need 3 of those components, but the components of that answer, the 3 components of the vector, actually has all 9 components of the tensor. So you can't just forget about 6 of the components of the tensor. Okay. Okay. Go ahead. Question over Zoom.
So is deformation just like the error in a Taylor approximation?
Yes. So the question over Zoom was, is deformation basically just an error in the Taylor approximation? Yeah, sure. Yes, I guess is the strict answer to your question. But I'm not sure if you're trying to imply something more than what you're saying. Are you trying to say that there are higher order terms in the Taylor expansion that we should be worrying about? Because if that's what you're saying, no, in general, we only care about the first order because we're talking about really small values of C. And so that shouldn't really, so the higher orders shouldn't really matter. But yes, I mean, this deformation comes about because, well, exactly what I wrote here. Different points experience different velocities. And so the Taylor approximation, the Taylor expansion is just a way to actually figure out what those, to express what those different velocities are. And in the process of that Taylor expansion, you get a velocity gradient. Okay. Okay. It turns out that this velocity gradient has two contributions. Okay, and this is because, as you guys have shown in your homework, any tensor has a symmetric and an antisymmetric component, right? Well, the velocity gradient here is a tensor, and so therefore it has a symmetric and an antisymmetric component, right? Those components look like this. There's 1/2 times this, plus 1/2 times this, right? With any sort of tensor, you can take the transpose of that tensor, and then you add together the tensor and its transpose, and then 1/2, that gives you the symmetric component. And if you subtract it, then you get the antisymmetric component. And hopefully you guys can see that if I actually go through the math and add these two together, this term right here will cancel with this term. These two terms actually will add up and will give me my exact original tensor. And perhaps you guys can see that for this particular term, if I switch the order of I and j, in other words, I take the transpose of this, I get the same thing. Here, if I switch the order of I and j, then I have to switch the order of subtraction as well, and so therefore you get the negative of itself, and so therefore this tensor is also antisymmetric. Okay? Now, in the language of velocity gradients, these antisymmetric and symmetric parts actually have a name. This symmetric part is called the strain rate tensor. And this antisymmetric part is called the vorticity tensor. Okay? This is the strain rate. It's symmetric. And this is called the vorticity. And this is antisymmetric. Okay? And I'm going to explain a little bit what those two contributions actually mean. Okay? First, I'm going to talk about what's happening on the right-hand side over here. This vorticity tensor that's related to a vector. Okay? You guys will show this in your homework. Okay? Or you've shown in your homework so far that for an antisymmetric tensor, that can be expressed in terms of a vector. You guys have shown this in your homework, right? Okay, cool. Makes intuitive sense to everyone, hopefully, because an antisymmetric tensor, as you know, has only 3 independent components, and a vector has 3 independent components. So hopefully you guys have thought about this. This is homework 1, or was this the previous homework? It was homework 2, homework 1, right? I'll say for an antisymmetric tensor. Okay, what you'll show in homework 3 is that for this particular antisymmetric tensor, you can also express that in terms of this, where my vector is now going to be called WK. And I need a factor of 2 to make the math work. Where now WK, or W, my vector, is actually just the curl of my velocity. Okay? And W is defined as the vorticity vector. Okay? And to tell you a little bit more about why we would do this and what those two tensors, the strain rate tensor and the vorticity tensor, actually means, let's actually look a little bit closer at what the velocity is near a point, my point 1, for instance, right? So I'll just write down, examine the velocity near my point x. Okay. How did that happen? Okay. Vj, evaluate x plus c, as we saw earlier, is equal to Vj of x plus the dot product of c and my velocity gradient. Okay. What I wrote right here, this equation, is exactly the same as this equation, except I'm expressing my velocity gradient in terms of these two different contributions. And so all I did was just substitute this guy in here. Okay. Now, using what I know now about my vorticity tensor, I can rewrite this equation. So this doesn't change. Okay. So this other piece now I can write like this. Okay. Because as you know, this capital omega ij is equal to this expression right here. Okay. All right. And so now I can actually, I'm going to manipulate this just one more time. This is the same. This is the same right here. But this guy now I can change. Okay, don't know how that happened. This guy here I can change into this. Right? You guys see how I was able to do that? To go from here to here. Multiplication is just commutative, and so it doesn't matter whether my c comes first, whether my half comes out, or whatever. That's all the same, right? So here's my c1, here's my wk, okay? And now epsilon ijk is the same as epsilon jki. Remember, my epsilon, I can switch two of those things, I take the opposite. So I switched I and j, and I switched I and k, and so I get jki, right? And the reason I did this is because now in non-index notation, this means this. V evaluate x plus c is equal to v of x. Man, this has a terrible time with parentheses. Plus c dot my strain rate tensor. Let me write a better strain rate tensor. Plus 1/2 times omega cross c. Okay. All right. And so what this means then is that, remember how this minus this is just my Taylor expansion, right? My v at x plus c equals minus v of x is equal to this guy right here, right? And so what that means then is right. Okay. So now that we did that, we can now maybe assign some sort of physical meaning to what these two contributions actually mean. Okay. To do that, let's go back to those 2 points again. So let's look at, let's assume that this is equal to 0, that we're not going to worry about the strain rate tensor, and only look at that term. Okay. Then our initial point goes from x to x plus v of x dt. Okay. And my second point goes from this to this. To this, right? This is the part of the velocity gradient that we've cared about, right? Remember, the second point right here, has a component. This is the deformation, the relative change between those points. That's c times del v dt. And what we showed over here is that c times del v has two components. One that's the strain rate tensor, and one that's this guy right here, right? And so that's why I have 1/2 omega cross c dt, lowercase omega, or w. Okay, and so what that means then, as we showed in this diagram up here, right? My original point goes from x to x plus vx dt, v of x dt. My second point goes from x plus c to x plus c v of x dt. Those two relative positions have not changed. The only contribution to the change in their relative position is this guy right here. This extra thing is this extra piece right here. And in this case, that extra piece is this. The change in relative position is now this. Okay. That's what that contribution actually means. What I'll point out is that omega cross c, that vector, is perpendicular to c. You guys believe me when I say that? Well, when I
Hey, Professor. We can't hear you over Zoom.
Can you hear me now? Over Zoom?
Yeah.
Great. Well, this is going to suck, but let's actually make this work. All right. When did you not hear me? I'll just mention that I mentioned over here that the cross product of omega and xi has to be perpendicular to my original xi right here, right? And so what that means is that the change in the relative position is perpendicular to the relative position. Okay. So in my diagram, if my original 2 points look like this, 1 and 2, I'm not going to draw all the different, like I'm not going to write like an x here and an x plus c. That just makes things cluttered. Okay. If my if after a time delta t now, right, this is what my original C looked like. This is my 1 prime, as I called it, and this was my 2 double prime, right? What this suggests is my actual new point 2 prime right here has a change in relative position that's perpendicular to my original relative position. So this point right here, or this vector right here, is my 1/2 omega cross C dt. Okay. And if these two vectors here are perpendicular, what that means is that the relative position between 1 and 2 should not change in magnitude, right? Assuming that that my C here is small enough, then this new vector here, which is the new relative position between the two of them, you can call this my C prime if you wanted to or whatever, right? That should have the same magnitude or same length as this original vector. Okay. What this means is that when my 2 points move, it's really hard to do with a microphone. I'm really sorry. When my 2 points move, instead what's actually happening is as they move, one of the points moves perpendicular to the relative position. And so what's happening is those 2 points are rotating relative to one another, right? And that's what this contribution, this omega contribution gives me, okay? Because my change in relative position is perpendicular to my original relative position, that means that my relative position between these 2 points is now angular. It's a rotation, okay? The other contribution, this strain rate contribution, is for any component of it that is not perpendicular to itself. Okay, and so that could be if my 2 points are moving, but now I have stretching of that C vector, if you will, and that's why that's called the strain rate tensor. And that's why this other component right here that we're talking about, the vorticity, is, well, it's talking about vorticity, it's talking about rotation or vortices or angular motion and stuff like that, right? So let me summarize that. My velocity vector, or the difference in my velocity vector, as you know, can be written like this in my Taylor expansion, right? And that velocity gradient tensor has 2 components. There's one from the strain rate tensor, and there's another one over here that comes about because of rotation. Okay. This first piece comes about because of changes in relative motion between the 2 points, or relative positions between the 2 original points. That's why it's called deformation. This other piece comes about from solid body rotation. Okay. And again, this gamma, this capital gamma right here, is called the strain rate tensor. Okay. What you guys will show in the next homework is that this solid body rotation, I can actually map out like, it's a rotation. And so if I have something that has a vorticity, then I could write like an angular velocity or something like that, right? And what you'll show is that the vorticity is twice the local angular velocity of the fluid. Okay. Okay. So let me just take a quick pause right here, because this is kind of an important concept where we've actually figured out what are the different components of my velocity gradient tensor. And if there's time, we're actually starting to near the end of the hour. And so I may or may not continue. Yeah, it's probably better if I actually just don't continue. talk a little bit more about how we relate this deformation component here to stresses and stuff like that. You could imagine just staring at this a priori, for instance, because this is about solid body rotation. As I mentioned, if I have 2 points and they're moving along, this contribution only tells you how they move, how they rotate. And so if these 2 points were in the middle of a solid, it could still move like that, right? If I were, if I were just sort of some object and we're moving along a fluid and it rotated or something, then that's totally, then that would be taken into account completely by this omega term right here, right? And so you can imagine then that by extension, there shouldn't be really much stress. There shouldn't be much of a stress involved inside the solid because it's a solid object, right? There's no relative motion between anything inside the solid, right? But then the deformation right here is where all the actual exciting stuff happens and allows us to relate stress to velocity and gives us more of those, gives us some of those 6 equations that we were talking about at the beginning of the lecture. Was there a question in the back? Sort of. So the question was, are we talking about the rotation of a ChE vector or something like of this ChE vector, right? We're not talking about the actual rotation, or we're not talking about any sort of curve motion or whatever of the individual points. We're talking purely about the relative position between these 2 points. So if I have my pinky and my thumb here, and the vector connecting going from my thumb to my pinky is ChE, right? What I'm saying is that if my strain rate tensor, my gamma term is 0, then what that means is when these 2 points move, they could just move like this and not move at all. But the only other way that they're now allowed to move is if they rotate, and the relative and the distance between my thumb and my pinky doesn't change, right? And that's just because the now change in relative, or the additional change in relative position between my thumb and my pinky now is encapsulated by this omega cross ChE. And that omega cross ChE vector is perpendicular to the original ChE vector. That's what I'm trying to portray with this diagram right here. It's as if, exactly. So the question is, it's as if we're applying angular momentum to ChE. It's as if someone went in and then took the ChE vector and then rotated it. And that's why I call it solid body rotation. And my point that the larger point that I was trying to make is that with solid body rotation, it's solid, right? And so if everything in my fluid is just rotating according to omega, then there's no change in relative motion between the two, or there's no deformation of the material inside this fluid. And if there's no deformation, then there's no relative stress between one element and another, right? It's as if the fluid is just moving as if it were a solid. It could be, instead of water moving from one point to another, it would be just ice moving from one point to another. The whole block of ice would just be rotating or whatever, okay? Where it starts to get interesting and where we actually start to get stresses and stuff is when we start talking about the strain rate tensor. And so on Friday, I think we're starting to run into the end of the class. On Friday, I'll talk about how we relate deformation here to the velocities and to the stresses and stuff. I am going to post a video on constitutive equations and rheology and stuff like that. Feel free to watch that video either before or after Friday's lecture. Okay. And as I mentioned, I will go back to my office now, get back on the Zoom call for anyone who's interested, including the people in class. We probably can't have in-person office hours, I'm sorry. And then if there are any additional questions, I'd be happy to address them. Okay. All right, thanks a lot.